Hello and welcome back to Power Series, Chapter 11, Section 2, Properties of Power Series. We're going to take a look at some really important stuff and set the tone for your differential equations, eventually. We know that the power series was defined as Cn x to the n, having the terms C0 plus C1x plus C2x squared plus C3x 3 plus ... going to infinity if you want to have the equal sign. And then we said we can center these power series, the Taylor series, at any value, because maybe we want to compute values that are away from 0. Maybe you need to compute 10.7. Well, center it at 10 and then compute 10.7, right? Or center it at 11 and compute 10.7. So it's important to do this. We also know, we've seen those, well, let's write the centered one. So that will be Cn x minus a, so for centered at a, and you have C0 plus C1x minus a to the first power, plus C2x minus a to the second power, plus C3x minus a to the third power, plus ... going on forever, because we are centering, right? We want infinitely many terms for exact calculation. So now that we know what the power series are, I'm going to call upon those graphs we had before, where you remember how the more terms you have, the functions bend closer and closer towards the function you're approximating. But eventually they always diverge from each other, right? Now, we also see this x inside the power series. And I'm going to write a very simple power series now. X to the n. No c's, just x to the n. From 0 to infinity. And I'm going to ask you about convergence of this one. Just the same convergence that you guys had in a previous chapter, convergence of series. Now, what can you tell me about the form of this problem? Looks like what? Geometric, very good. Your geometric was AR to the n. Let's just get rid of A and let's call R X, and there you go, right? So it looks like geometric. So now, what does that mean in terms of convergence? Beautiful. So to converge, x must be between -1 and 1, and to diverge, x needs to be smaller or equal than -1 or larger and equal than +1, right? What we have found is what we call interval of convergence, right here. You see, when you pick an x value, say 5, if you pick x value as 5, you will have 5 to the x. And you know that diverges by geometric series test, right? If you pick a value to be 1/3, not raised to the x, sorry, raised to the n, raised to the n, then it converges by geometric series test. So convergence and divergence of power series depend also on a choice of x. Not just, oh, it's a geometric series and what is the value? Because it's a geometric series, but geometric series converge and diverge for different values of, in this case, x, but it was r in a previous section. So when you get a power series, you get to ask yourselves, what values of x would make that series converge, and what values of x would make it diverge? And you don't want the divergent ones. You just want the convergence, right? So what do? We are talking about interval and radius of convergence of power series. Now, I have to steal the 3 problems that are done in the book because they are absolutely awesome, and pretty much every book is using the same problem, same setup. I don't like doing that because you can always read, but I need the 3 so we can make the contrast between them. So first one, A. Summation of x to the n divided by n factorial from 0 to infinity. That's a power series. And as a matter of fact, that's e to the x. That's power series e to the, when I look at that, I see e to the x. It's a power series for e to the x. So, for which values of x will this power series converge, and for which would diverge? Well, we are looking for interval of convergence, and that will give us, like, half of that would be the radius of convergence. So let's take a look. What I do here is I'm going to do the ratio test. We always use ratio test, unless you can do the root test, it's easier. So we use ratio test to find interval of convergence. So we use ratio test for that. So what do? Well, I know that my an is x to the n over n factorial, and I know that I need n plus 1, which is x to the n plus 1 over n plus 1 factorial. Ratio test from last night, I hope you learned it already because it's so damn important. Limit n goes to infinity. We take our xn plus 1 over n plus 1 factorial, and we divide that or multiply it by the flip of the, right, because we do the limit of an plus 1 divided by n plus 1 by an. That's the test. But then, and in absolute values. I may put those in blood. You absolutely must have them now. You'll see why. So we take the denominator an, we flip it into multiplication. Now we do peeling and canceling. So on top I have x to the n times x. In denominator I have n plus 1, which peels off, then n factorial, times n factorial x to the n. These guys cancel, these guys cancel. And I am left with the limit n goes to infinity of x divided by n plus 1. Now, n plus 1, and all n's are positive values because it starts at 0 and goes to positive infinity. X could be positive or negative. Now, the limit performs its operation on n. That's the variable for the problem. So we are allowed to kick x outside as a constant and just focus on limit n goes to infinity of 1 over n plus 1. which is absolute x times 0, which is 0. Now 0 is always less than 1. We know that's our ratio test. So, conclusion, power series, summation x to the n divided by n factorial, 0 to infinity, converges for all x, which means interval of convergence is negative infinity to positive infinity, and radius of convergence is r equals infinity. This problem was centered at 0, so if you have your x-axis like this and it was centered at 0, you have radius of convergence to be infinity, and then the other side is also infinity, so radius of convergence is infinity. No matter what x you pick, you will always have a convergent series here. Now that makes sense because look at the form of the power series. Pick x to be 10. You are going to have 10 to the n divided by n factorial. Didn't we say that factorials are much faster in terms of, right? So it's going to force this into convergence. Pick 0.06 to the n divided by n factorial. Doesn't matter what you pick for x value. It will always converge, because you will always have exponential divided by the factorial, and the factorial converges much faster, grows much, much faster than exponentials. Therefore, it doesn't matter what x you are picking, you will always be getting convergence, doesn't matter, positive, negative, and that's why our interval of convergence is from negative infinity to positive infinity. That says that you can pick any x value, you will always have convergent series. Now, series B, they put in a little bit spice in there. They put negative 1 to the n, x minus 2 to the n, divided by 4 to the n. That negative 1 to the n was completely unnecessary, but let it be. Again, what are the values of x for which this problem is going to converge? Now, let's ignore negative 1 to the n for a little bit and just try values of x. We are just completely ignoring this piece now. Say x equals to 10. 10 minus 2 is 8. So you have 8 to the n divided by 4 to the n, which gives you 2 to the n. If I pick a 10 as a value, I get divergent geometric series, right? How about if I pick 4? Say x equals 4. If x is equal to 4, then I have 4 minus 2 equals 2. I get 2 to the n divided by 4 to the n. That's 1/2 to the n. Oh, that's convergent. So in this case, certain values are going to make converge and certain x values are going to make a diverge. I want to find exactly where are those cutoff points, which we call interval of convergence. Where are those cutoff points where this problem becomes convergent, and what are the other values that make it divergent, right? So how do we do this? We don't need any of this stuff. This is just me talking about what we are trying to achieve. We do this using the ratio test. You have your an, x minus 2 to the n divided by 4 to the n. We are ignoring this piece because the ratio test has absolute values. It kills it, right? An plus 1 is going to be x minus 2 to the n plus 1 divided by 4 to the n plus 1. Ratio test. Limit n goes to infinity. Absolute value. This problem, you must have it. Now we do the a plus 1. So we have x minus 2 to the n times 4 to the n. So this is that plus 1 peeled off already, times the flip of the original series, because it was in denominator, now goes in the numerator, so it flips. Cancel x minus 2 to the n, x minus 2 to the n, x 4 to the n, 4 to the n. Nice one. And what you're left with is the limit n goes to infinity of, and now you have x minus 2 divided by 4. Well, there are no n's. And since there are no n's, well, we'll just drop the limit, because limit is supposed to operate on n's. N's are no longer with us, right? So all I have is absolute x minus 2 divided by 4. Now, I want convergence, so I am going to set this less than 1. Because for ratio test, we know that the limit needs to be smaller than 1 in order for us to have the convergence. So I'm going to do this here. We set this less than 1 because we are looking for convergence. So before, when you had n and all of this stuff in the previous chapters, you compute the limit comes out to be a number, or smaller or larger than 1, and you claim convergence and divergence, right? Now you are looking for convergence, so it's up to you to set it less than 1. Just like you were setting your derivative equal to 0 to find min and max, right? Remember that? Do you remember Calc 1? To find min and max, you find the derivative, you set equal to 0. So now, to find integral convergence, you set the ratio test less than 1, because the test is convergent if it's less than 1. And now you have algebra 1 inequality to solve. You learn absolute values, inequalities in your algebra class. You know that you are supposed to do this. I mean, you're sitting in Calc 1, so in Calc 2, so you should have passed algebra at some point. So you write it this way, then you multiply everywhere by 4. And then you add 2 everywhere to get x alone. This puppy over here, which is negative 2 to 6, is known as interval of convergence. Any number you pick from here as your x will have your power series become a convergent geometric series. Any value you pick will work. Any value outside of this range would make it into a divergent series, geometric series. Now, we need to calculate the radius of convergence as well. Well, you have the interval from -2 to 6. Half of that integral, use common sense, half of that integral better be where your series was centered. And it was centered at A, right? If you have 2 units to the left and 6 units to the right, that's 8 units in length. Half of 8 units in length is 4 units. 4 units, 6 minus 4 is 2. Or -2 plus 4 is +2. Your problem, when you started, was centered at 2. Because remember, your centering is x minus a. If it's x minus a, and this is x minus 2, then your a is 2. And that's the center. That has to be the center of the interval. So radius over here is 4. Radius of convergence is 4 because you have 4 units to the left and 4 units to the right. Now that's technically a gift, obviously. As soon as you have your radius, your interval of convergence, radius of convergence is half of that interval. So 4 units to the left and 4 units to the right from where this damn thing is centered at. So this is how we find interval and radius of convergence. Previous problem had infinite interval and radius, meaning any x you pick under the sun will make the power series converge. Now, in this second example, part B, only the numbers that you pick between -2 and 6 as x would make it converge, and all other numbers would make it diverge. And now we have the third example, part C. This one is summation 0 to infinity of n factorial times x to the n. Oh, so it starts at 1. It starts at 1. Okay. We do the ratio test right away. That's how we look for radius of convergence. Your an is n factorial x to the n. Your an plus 1 is going to increase every n by 1, so n plus 1 factorial times x to the n plus 1. We have our ratio test, limit n goes to infinity. Absolute value. We take our n plus 1 factorial x to the n plus 1, and we divide it by n factorial x to the n. We do the peeling and canceling. So peel off these plus 1s. We have n plus 1 times n factorial times x to the n divided by n factorial x to the n. Cancel and cancel, and you are left with the limit n goes to infinity of absolute value of n plus 1 times x. We get to kick absolute x out of the limit, just like we did in the first example, because the limit operates on n's, and we get to take the limit of n plus 1. What's the limit of n plus 1 as n goes to infinity? Infinity. You are technically getting absolute x times infinity, right? Is this convergent? The answer is yes, at a single point. If x is equal to 0, it's going to zero everything out, and it's going to be convergent, right? But that's just going to also kill your power series if x is equal to 0, right? So this converges for a single point, x equals 0, and diverges for all other x's that you have. So now we say, when x equals 0, we have convergence, all other x all other x different than 0. Boom, divergence. What's my interval of convergence? Single point. So interval of convergence is x equals 0, single point. Radius of convergence r equals 0. There is no radius to it. It's just a single point for convergence and the infinity around it for divergence. So now the problems that you get here are threefold, right? You have problems where any x you think of converges. You have problems where you have an interval, some values on the interval make it converge and others diverge. And you have this case where all but one point or even all values make it diverge. So that's our property of convergence, where the power series can be converted into regular series, whether they are geometric or whatever else, and we use the ratio test there to solve them. So now, what's the rest of the power series properties? Theorem 11.4. These are the ones that you guys need so you can survive your differential equations. So, theorem goes like this. Suppose that f of x is a convergent series, Cn x to the n, right, it's infinite, and g of x is, well, let's put underneath, and g of x is the summation d of n x to the n. Again, it's the infinite series. They can start at 0, they can start at 1, they can start at 6. So I'm not going to put anything on the bottom. It's just that they're infinite series, they're power series. So number one, sum and difference. If you have summation of Cn x to the n plus or minus dn x to the n, that's going to work out to be f of x plus minus g of x. Exactly what you expected right on the other end. Remember how in my differential equation that I showed you earlier, I replaced the derivative with a power series, then I had minus, and then another power series for y, right? So you can combine these guys into a single power series. Number two, multiply by a power. We don't have problems for this right now. Wait for Euler's equations and some other to see if the power series in DFQ, you'll be sick of this. You have x to the power m in front of the series Cn x to the n. You can ship this one inside to have the power series Cn x to the m plus n. You know this formula, m plus n, from algebra. When you multiply x to the m times x to the n, you get x to the m plus n. Now, this x to the n is trapped by the series, so that one cannot come out because the series operates on n. But this one is m, that one can come in and leave as it wants because the series operates on it. Do we have any math majors? No? Well, I guess you won't see the two-dimensional series where there is a series that operates on m and n, and then nothing can escape. right? You can bring in a third one if you want to, but these two have to stick inside. A nested series, series inside a series. There are whole courses based on these things called asymptotics, asymptotic behavior, whatever, 700 level courses, asymptotics 1 and asymptotics 2. They're really cool things. You get nested power series, series within series, and you keep expanding. They can go and nest as many times as they want, because I think, yes, not the real preview of it, but kind of scratching the surface composition. Remember how one series represents f of x and the other series represents g of x? Well, can't I just plug g of x into the f of x? That means that every x of your power series of f is replaced by the power series of g. So when I go here, this one becomes the power series, this one becomes the power series, this one becomes the power series. So all of those, because they all become g first, and then g has its own power series to put in, right, for each one of those. So that's going to be nested power series. Now, it's not just f composed with g. You can compose f with g with h, right? So you can keep composing and nesting power series like this all the way down till you run out of the will to live. Now, this one over here is a simple case where they give you that h of x is equal to bx to the m. And you can import that into power series Cn, right? We have the Cn. And now instead of x to the n, you are going to have bx to the m, everything raised to the n. That's just a composition where you are replacing the good old power series Cn x to the n to the one using the composition. Now, this composition part is the one that is going to greatly help you solve certain really nasty problems. Say that for some reason you love pain and you want to integrate sine of x cubed dx. Is it a trigonometric integral? No. Is it a u sub? No. Is it a trig sub? No. Partial fraction decomposition? No. Nothing works. There are no power reducing formulas because the cube is not on sine, cube is on x. Right? If cube was on sine, it's a joke. You peel off one sine, you make sine squared into 1 minus cosine squared. You should be able to do that problem mentally at this point in Calc 2 if the cube was on sine. But the cube is not on sine, cube is on x. And you don't have x squared in front for u sub. You don't have anything in front for integration by parts, so you can just stare at this and cry. That's it, right? Now, what power series do is, which is our next and last section, power series swoop in and make a joke out of this problem. See, power series for sine, this is the skill that we need for the last section. Power series say your sine can be written as a polynomial and just, use few terms and throw in the garbage the rest. So x minus x cubed over 6 plus x to the 5 over 120. Just to keep the first, let's say, 3 terms. Now that's sine x, where this x is this x and this x and this x, right? But I don't have sine x. I have it cubed, right? So what I'm going to do is I'm going to now replace every of these sine x's with sine cubed. So that's going to be x cubed minus x cubed cubed over 6 minus x cubed to the 5 over 120. Do you see the hack? And what you have is x cubed minus x to the 9 over 6 minus, no, sorry, this is a plus x to 15 over 120. So now if you want to integrate this, you take this polynomial, this joke, and you replace this with it. And this is why you don't need anything you learned prior to this one, because anything that all your trig substitutions and all of your stuff, that's going to be the power series 11.4. There's a little bit more to it, so we're going to restart this problem and restart the stream. Literally, it's going to take me 5 to 10 minutes to go through that section. But just realizing that all you are doing now is, if you are able to come up with the power series for the function that you are looking at, you are going to replace that crazy function with this polynomial that you get, and then differentiating and integrating becomes a joke. No more power rule, no more chain rule, no more any of the integration techniques, because you will just be cranking derivatives and integrals on basic polynomials. Sure, their exponents are going to be high and crazy, but who cares? Right? It's a derivative or integral of a polynomial. So let's restart this.